After studying this module, you shall be able to know about the significance of mass spectroscopy, the basic principle and instrumentation of mass spectroscopy, the methodology and applications of mass spectroscopy. Mass spectrometry is an impressive analytical technique used for identification and quantification of wide range of chemical and biochemical compounds. This technique is subtle enough to detect minor mass changes in the compounds, allowing for their structure elucidation. In mass spectrometry, the molecules are converted into gaseous phase ions and separated on the basis of their mass to charge ratio, that is m/z. The ions move towards the detector under the effect of magnetic and electric field and get segregated as per their mass by charge ratio. The result is achieved in the form of mass spectrum, which represents the relative abundance versus m/z ratio of a sample. The ionization methods used frequently for majority of biochemical analysis are electrospray ionization and matrix assisted laser desorption ionization. Both negatively as well as positively charged sample ions can be created using most of the ionization methods. Now we will see the basic principle of mass spectrometry. The annihilate molecules are converted to gaseous phase and bombarded with high speed electrons so that they are ionized. These ions are separated in space or time based on their mass to charge ratio and are quantified. All the ions are accelerated across the same distance by same force, therefore have same kinetic energy determined by the acceleration voltage of the instrument V and the charge of the ion Z, and the kinetic energy is given as the product of the charge of the ion and voltage, which is equals to half mv square, where m is the mass of the ion and v is the velocity of the ion. As charged ions move through the magnetic field, they are bent in an arc to follow a circular path of certain radius in the direction perpendicular to the applied magnetic field. Here, the magnetic force Fh on the ions is balanced by the centripetal force Fc and is given as Fh is equals to the product of charge of the ion into velocity of the ion into magnetic field, which is equals to the centripetal force Fc, which is equals to mass into square of velocity divided by r. On rearranging the equation, we have another expression for velocity of the ion, and ultimately we have expression for m/z as square of the magnetic field into r square divided by 2 into voltage, and we have r is equals to 1 upon magnetic field under root 2 into mass into velocity divided by the charge of the ion. The ions of a certain m/z value have a unique path radius which can be determined if both magnetic field magnitude h, acceleration voltage v are held constant. All ions having same m/z values are deflected to the same degree and follow the same trajectory. Components of mass spectrometer. The major components of mass spectrometer are sample inlet. The gaseous phase sample ions are introduced into ionization source of the instrument through sample inlet. Common method for sample introduction is direct vapor inlet, in which the high vapor pressure gas phase sample is introduced directly into the source region through a needle valve. Supposing the annihilate decomposes at high temperature, meaning that it is thermally labile or that the sample does not have enough adequate vapor pressure, then it must directly be ionized from the condensed phase. The sample can also be introduced to the ionization source through a chromatographic system such as coupled high pressure liquid chromatography termed as HPLC or gas chromatography termed as GC instrument. Ionization source. The sample molecules are excited so that they eject an electron to form a radical cation or are forced to undergo ion molecule reactions to produce adduct ions, mostly by addition of a proton to the molecule. We have this reaction. The amount of fragmentation is controlled by substantial ionization energy observed in the mass spectrum. It offers structural information for the identification of unknown compounds in spite of the complications produced in mass spectrum due to extensive fragmentation. Some ionization methods are easy and only produce molecular ions. Other techniques known as hard ionization techniques are very active and cause ions to undergo extensive fragmentation. The ionization method to be used depends upon the type of sample under investigation and the mass spectrometer available. For gas phase ionization, the two suitable techniques are chemical ionization and electron ionization. For the ionization of the condensed phase samples, various techniques used are matrix assisted laser desorption, secondary ion mass spectrometry, fast atom bombardment and electrospray. Now the next component is analyzers. The ions are accelerated into the mass analyzer with the help of an electric field immediately after their formation. Resolving the ions which are formed in the ionization source according to their mass to charge ratio is major function of mass analyzer. These mass analyzers have different features including the range of M by Z analyzed, the mass accuracy, detection limits, resolution and scan rates. Analyzer can be considered as continuous or pulsed. A specific single M by Z is transferred to the detector by the continuous analyzers and by scanning the analyzer. Mass spectrum is acquired such that varied M by Z ratios ions are detected. These analyzers consist of quadrupole filters and magnetic sectors. These analyzers work on single ion monitoring which improves the signal to noise ratio. Pulsed mass analyzers collect an entire mass spectrum from a single pulse of ions. Since all the ions are detected, these analyzers have very high transmission efficiency which increases the S by N, that is signal to noise ratio. Pulsed analyzers include time of flight, ion cyclotron resonance and quadrupole ion trap mass spectrometers. There is a variation between compatibility of different ionization methods and different analyzers. For instance, all of the analyzers listed can be used in combination with electrospray ionization, whereas for instance, matrix assisted laser desorption ionization is usually coupled to a TOF analyzer. Tandem mass spectrometers consisting of two mass analyzers have been developed for sophisticated structural and sequencing studies of complex macromolecules like proteins. In these instruments, the first analyzer is used as a mass filter to isolate a molecular ion that will enter the collision cell where it is fragmented. The second mass analyzer analyzes the resulting fragments measuring their molecular mass. Commonly coupled tandem mass spectrometers include quadrupole, magnetic sector quadrupole and the quadrupole time of flight analyzers. Ion detectors. The ions sorted by analyzer strike the detector where the signals are amplified and transmitted to the data system. For the generation of mass spectrum, the M by Z values of the ions are plotted against their intensities, which presents molecular mass of each component, number of components and relative abundance of various components in the sample. Common detectors used in mass spectrometers are the photomultiplier tube, the electron multiplier tube and the microchannel plate detectors and Faraday cup. High vacuum system. Since mass spectrometers use gas phase ions for analysis, they operate in a high vacuum system, typically from 10 to the power of -2 to 10 to the power of -5 pascals, often maintained by a pumping system. The ionization source, analyzer and detector of the mass spectrometer are maintained under high vacuum so that the ions travel smoothly through the analyzer to the detector without any hindrance. This also minimizes the chance of collision of ions with other molecules so that they do not react, scatter or fragment. Now we will learn about the interpretation of mass spectra. Analyzing the peaks. A mass spectrum is presented as a bar graph in which the relative abundance of ions taken on the ordinate is plotted against mass to charge ratio taken on abscissa. Most of the ions made in a mass spectrometer have a single charge, so the m/z value is equal to mass itself. Modern mass spectrometers provide totally accurate values regarding the molecular mass of the compound by easily resolving ions which differ even by a single atomic mass unit. Molecular ion peak or parent peak. The molecular ion is easily identified as the ion with the highest m/z value unless it represents an impurity or an isotopic ion. The parent peak represents the mass of molecular ion reduced by loss of an electron. Conventionally, it is used to calculate the molecular weight of compound using the masses of most abundant isotopes of all the elements present in it. It is often too weak to be seen in the high energy spectra that necessarily bring about fragmentation of the molecule. The intensity of molecular ion is high for chemically stable molecule. Molecules containing pi bonds tend to generate more stable ions. Therefore, the relative height of parent peaks of some classes of organic compounds can be presumed to decrease in the following order. That is, from aromatic to alicyclic, to ketones, to amines, to esters, to ethers, carboxylic acids and alcohols. Fragmentation and base peaks. Due to bombardment with high energy electrons, molecules often undergo fragmentation and thus the parent peak is either weak in intensity or is completely missing from the spectrum. The molecular ions are energetically unstable and some of them cleave into smaller fragments. The most intense peak in the spectrum is the base peak, which refers to the ion with the greatest abundance, assigned as 100%. The height of all other peaks are measured with respect to the base peak. Cleavage is more likely to occur at carbons exhibiting higher degree of branching and reflect the stability of the ion. The structural information about the molecule can be obtained from the fragmentation pattern of the mass spectrum. Isotopic peaks. Many elements have more than one naturally occurring stable isotopes which produce peaks in the mass spectrum other than the main peak, the one due to the most abundant isotope. Molecules having high isotopes give peaks corresponding to their m/z values, that is, peaks occurring at m+1 or m+2. The intensity of these peaks are relative to their natural abundance. For example, the isotopes of chlorine 35 and 37 occur in the abundance ratio of 75.8 is to 24.2, and their peaks give the intensity ratio of 100 is to 31.9. Now we will see the application of mass spectroscopy in forensic science. Toxicological analysis. One area where a mass spectrometer is accessible is in the cases involving poisons or drugs. Forensic analysts can take samples of a subject's tissue or bodily fluid and determine if any toxic substances are present, and if so, in what concentration. This can give vital clues to investigators as to how a victim died, as well as help identify the time and dosage of any poison or medication ingested. Investigators can also determine if a victim was a regular user of any substances that might have contributed to his or her death. Trace evidence. Mass spectrometry is also beneficial in examining trace evidence. Investigators at a crime scene may find microscopic materials like carpet fiber, glass splinters, or paint flakes. Ordinarily, these substances might be extremely difficult to use as a starting point to identify a suspect. However, a mass spectrometer can determine the precise mix of dyes used in carpet fibers, the makeup of materials that went into any particular glass fragments, and the precise set of polymers present in any paint sample. This information can lead investigators to a particular manufacturer who may be able to narrow down where a given sample came from, helping detectives to identify suspects and build a case. Arson investigations. Arson investigations can also benefit from the use of mass spectrometry. While an arson investigator might be able to identify the use of an accelerant through burn patterns or lingering odors, a mass spectrometer can break down any residue and provide an accurate report of its molecular makeup. This can help identify any unique or exotic compounds that may be present. Discovering a similar mix used at multiple crime scenes may be useful for identifying the work of a serial arsonist. Explosive residue. Another area where spectrographic analysis is extremely useful is analyzing explosive residues. When a bomb detonates, it may not leave behind much in a way of physical evidence, perhaps only small fragments and chemical residues. However, commercial explosive manufacturers each utilize their own unique mix of chemicals, and a spectrometer can analyze this residue to identify the particular makeup of the explosive involved. Even in cases where a bomber used a homemade mix, the analysis may identify the type of material used and give investigators a push in the right direction to identify the source. Mass spectrometry is an impressive analytical technique used for identification and quantification of wide range of chemical and biochemical compounds. The ionization techniques used frequently for majority of biochemical analysis are electrospray ionization and matrix-assisted laser desorption ionization. The gaseous phase sample ions are launched into the ionization source of the instrument through sample inlet. The mass by charge values of the ions are plotted against their intensities to generate the mass spectrum, which shows the number of components in the sample, the molecular mass of each component, and the relative abundance of various components in the sample. Molecular ion peak is used to calculate the molecular weight of compound. The most intense peak in the spectrum is the base peak, which refers to the ion with the greatest abundance and assigned as 100%.